Hello my friends, and welcome back to the You Can Do TV channel. Hidden deep within the Swiss Alps, the Detention project stands as a benchmark in underground hydropower engineering, where scale, precision, and endurance converge over nearly a decade of construction. More than 400 workers operated in high-altitude conditions, advancing a vast network of 17 kilometers of tunnels carved through solid rock. Excavation alone reached approximately 1.7 million cubic meters, achieved through controlled drilling and blasting sequences, followed by systematic rock support and lining to stabilize the underground environment. At the core of the project lies a massive cavern housing the powerhouse, where reversible pump turbines are installed to enable pumped storage operation. This system allows water to be cycled between reservoirs, storing energy and releasing it on demand with high efficiency. Logistics and sequencing proved critical, as excavation, transport, and installation activities had to be synchronized within confined underground spaces. With a capacity of 900 megawatts and annual production of around 2.5 billion kilowatt-hours, Detention represents a strategic energy asset, delivering flexible, large-scale storage for Europe's evolving power grid. The year 2014 marked a decisive transition phase for the Detention pump storage project, as construction shifted from large-scale excavation to advanced electromechanical installation. After years of continuous underground work, the completion of most of the 17 to 18 kilometers tunnel network created the structural backbone required for the next engineering stages. One of the most significant milestones was the completion of the massive underground powerhouse cavern, located approximately 600 meters beneath the surface. Stretching nearly 200 meters in length, this vast chamber ranks among the largest underground spaces in Europe and was designed to house 6 high-capacity pump turbine units. This achievement signaled a clear transition from geological excavation to precision-driven energy infrastructure development. At the same time, major surface works accelerated, particularly the raising of the Vieux-Emerson Dam by about 20 meters. This upgrade significantly increased reservoir capacity, effectively transforming the dual reservoir system into a large-scale energy storage facility capable of balancing electricity supply and demand. Workforce dynamics also evolved throughout 2014. Mining crews gradually gave way to mechanical engineers, welders, and electrical specialists. With up to 500 workers operating simultaneously in challenging alpine conditions, logistics and coordination became critical factors. Overall, 2014 established the foundation for system integration and future commissioning, bringing the 900 megawatts energy project closer to operational reality. Spanning the River Mersey, the Silver Jubilee Bridge is a steel arch structure connecting Runcorn and Widnes in the UK. Completed in 1961, it features a through-arch design that carries traffic along a suspended deck. Engineered for durability and load distribution, the bridge has undergone major refurbishment to extend its service life, incorporating structural strengthening and modern safety upgrades. Innovation in the Brenner-based tunnel focuses on a highly specialized solution for constructing the tunnel invert. At the core is a custom-developed automated invert formwork carriage, engineered to deliver high precision and continuous productivity over approximately 10 kilometers of concrete works. This 130-ton, 55-meter-long machine enables the casting of double blocks per cycle, placing up to 90 to 95 cubic meters of concrete, along with 12 tons of reinforcement cages. A key engineering feature is its advanced running gear, designed to limit ground pressure to just 2 N per square millimeter, protecting freshly poured concrete, comparable to aircraft-grade load distribution systems. The system operates on a 24-hour cycle. Formwork is positioned with centimeter accuracy, while transverse adjustment allows fine alignment within plus or minus 50 millimeters. Prefabricated reinforcement cages are then installed, ensuring structural tensile capacity, followed by controlled concrete placement and surface finishing. After curing, the carriage advances roughly 25 meters to begin the next sequence. By integrating automation, precision alignment, and efficient material handling, this prototype significantly enhances construction speed, quality consistency, and operational safety within one of Europe's most complex tunnel projects. The standout engineering feature of the T30 Hotel lies in its advanced seismic resistance system. The structure uses a diagonal steel bracing framework that distributes seismic forces across the entire building, reducing stress concentration at critical. Unlike conventional rigid frames, the modular system incorporates high-strength bolted connections and energy-dissipating joints, allowing controlled movement during an earthquake. This flexibility prevents brittle failure while maintaining overall structural integrity. Each prefabricated module is integrated into a unified load-bearing system, forming a resilient, continuous structure. Tested by national research institutes, the building achieves significantly higher seismic performance than traditional designs, enabling it to withstand extreme ground motion while protecting occupants and critical systems. In Geneva Marine and Verrier, a forward-thinking construction approach is redefining how concrete is managed on site. Instead of demolition and disposal, existing slabs undergo micromilling, high-pressure cleaning, and surface treatments such as bouchardage to restore structural integrity. The slabs are then cut, screened, and carefully prepared for reuse, ensuring they meet performance requirements. This coordinated process allows materials to be reintegrated directly into new works, reducing waste and transport demand. By prioritizing on-site material revalorization, the project significantly improves environmental performance while maintaining technical standards, demonstrating how circular construction practices can be applied at scale. On complex infrastructure sites, access defines efficiency. This is where the boom lift aerial work platform becomes essential. Designed for high-reach operations, this equipment uses an extendable arm to position workers precisely at elevated or hard-to-reach locations. Commonly deployed for bridge maintenance, structural repairs, and equipment installation, the system provides both vertical and horizontal reach. The integrated work basket ensures operator safety, equipped with guardrails and stable controls. Branded as Verint, the machine emphasizes reliability and maneuverability, allowing crews to operate efficiently in confined or elevated environments while maintaining strict safety standards. A major milestone has been reached with the completion of HS2's longest tunnel beneath the Chilterns. Constructed as a twin-bore system, excavation began in 2021 using high-performance tunnel boring machines, advancing at an average of 16 meters per day. Each TBM installed precast concrete segment linings as it progressed, forming a continuous structural shell. Along the route, ventilation and access shafts were constructed to regulate airflow and provide critical emergency entry points. Following breakthrough, work shifted to internal fit-out, including walkways, drainage, and service systems. Excavated material was carefully managed and reused, supporting sustainable construction practices. This tunnel now forms a klutsch segment of the future high-speed rail network. The Fisher Border Wall project in El Paso, Texas, demonstrates a fully integrated infrastructure approach, combining heavy earthworks, structural installation, and advanced monitoring systems. Within just 4 days, crews completed large-scale grading operations, preparing the foundation for both the bollard fence and an accompanying concrete patrol road. The system extends beyond a physical barrier. It includes drainage control, electrical networks, and fiber optic cables capable of detecting footsteps and tunneling activity. Steel bollards are fabricated using weathering steel, significantly extending service life to approximately 80 years, while reinforced concrete foundations ensure long-term stability across rugged terrain. Challenging slopes, ranging from 18% to over 30%, required synchronized deployment of excavators, concrete paving crews, and installation teams advancing uphill in sequence. The project integrates lighting, surveillance cameras, and access roads, enabling continuous monitoring and rapid response. This coordinated, vertically integrated execution ensures durability, operational efficiency, and enhanced border security performance. The track demolition at Romerhofplatz. Phase 1 represents a large-scale urban infrastructure operation, executed with high equipment density and precise coordination. Over a 480-meter section, approximately 110 personnel from KIBAG deployed a mixed fleet, including 2 large excavators up to 100 tons, 8 wheeled excavators, 10 to 22 tons, and 8 crawler excavators, 26 to 40 tons, supported by 44 trucks for continuous material hauling. Initial operations focused on asphalt and track removal, generating around 300 tons of pavement waste and 700 cubic meters of concrete debris. Excavation works followed, removing roughly 900 cubic meters of material, while simultaneously delivering an equal volume of gravel for sub-base preparation. The use of dozers equipped with 3D control systems ensured precise grading and alignment during reconstruction. Beyond demolition, the project included installation of 1,000 meters of utility lines, along with 16 sludge collectors and 14 cable shafts, integrating drainage and electrical infrastructure. The workflow combined demolition, excavation, transport logistics, and utility installation in a tightly sequenced process, minimizing disruption while maintaining high productivity in a constrained urban environment. The Lamar Towers project, January 2015 in Jeddah, represents a large-scale high-rise development characterized by complex structural sequencing and intensive vertical construction. Designed as twin towers overlooking the Red Sea, the project relies on reinforced concrete cores, combined with floor slab systems to achieve both height and structural stability. Construction progress during this phase focused on core wall advancement using climbing formwork systems, enabling continuous vertical casting with controlled cycle times. Tower cranes played a central role in material logistics, handling rebar cages, formwork panels, and concrete delivery to elevated levels. The integration of multiple cranes ensured uninterrupted workflow across both towers. Floor slabs were constructed in tandem with the cores, utilizing repetitive formwork and staged pouring sequences to maintain alignment and structural integrity. Coordination between vertical and horizontal elements was critical to avoid delays and ensure load transfer continuity. Facade preparation and early installation phases also began, requiring precise anchoring systems embedded during structural works. The project demanded strict scheduling, as high-rise construction introduces challenges related to wind loads, vertical transport, and safety at height. Overall, the Lamar Tower's development highlights advanced high-rise engineering practices, combining efficient formwork technology, heavy lifting logistics, and synchronized construction processes to deliver large-scale urban infrastructure in a demanding coastal environment. The large block girder erection over the E91 Yamato-Takata bypass illustrates a highly controlled bridge construction sequence, integrating modular fabrication, constrained site assembly, and precision heavy lifting. Steel girder segments, fabricated off-site in Toride, were delivered by trailer and reassembled within a narrow staging yard confined between a retaining wall and adjacent private structures. This limited workspace required meticulous planning of assembly positions, lifting paths, and clearance envelopes to mitigate load sway during hoisting. Segments were connected using splice plates and high-strength bolts, forming a 47-meter integrated girder. Throughout assembly, dimensional control was rigorously maintained using surveying instruments to ensure compliance with final geometry tolerances. Parallel to girder preparation, composite deck elements were installed in advance to reduce on-bypass work. Steel plate panels, functioning both as permanent formwork and structural deck components, were aligned, bolted, and fitted with side plates to define slab boundaries, streamlining subsequent concreting operations. The erection phase was executed through a strictly controlled nighttime road closure window. A 750-ton crawler crane, Liebherr LR1750, lifted the 167-ton girder under extremely tight clearances of approximately 70 centimeters from adjacent structures. The operation required lifting to nearly 19 meters, followed by slewing and load retraction within a 20-meter working radius. Crane performance was dynamically adjusted through boom configuration and counterweight control to maintain stability and avoid interference. Real-time coordination was achieved via radio communication, with ground crews managing taglines to suppress rotation and lateral drift. The girder was carefully aligned, temporarily bolted to previously installed sections, and seated on elastomeric bearings atop a concrete pier. Subsequent tasks included scaffold erection and installation of brackets and longitudinal members. All operations were completed within the 9-hour closure, demonstrating advanced logistical planning, precision engineering, and disciplined execution under constrained and high-risk conditions. The Matrix 502 asphaltic expansion joint system installation follows a precise. The procedure begins with marking and saw cutting a 20 to 24-inch wide section down to the concrete deck with a minimum depth of 2 inches. Surface preparation is critical. The substrate must be dry, clean, and properly profiled, often requiring abrasive blasting and hot air drying. Backer rods are installed, followed by application of hot binder at 380 to 410 degrees Fahrenheit, forming a thin sealing layer. Steel bridging plates are then positioned over the expansion gap and embedded into the binder. A heated aggregate binder mix is prepared at controlled ratios and placed rapidly into the joint. The material is leveled and compacted, using heavy rollers to achieve full density. Final steps include surface heating, binder coating, and spreading of dress aggregate for skid resistance. After cooling, typically within 1 to 3 hours, the joint is ready for traffic, delivering a flexible, watertight seal. HS2 has completed the first permanent pier of Curzon No. 3 Viaduct in Birmingham, marking a major milestone in the city center project. The 300-meter viaduct is the final structure in a series of 5 Curzon approach viaducts, stretching from Duddieston Junction to Curzon Street. The construction sequence follows the trial pier, with prefabricated reinforcement cages lifted into orange formwork before pouring. In total, 30 reinforced concrete piers ranging from 5 to 6 meters high will be built, along with 4 steel tripods over Digbeth Branch Canal. Eco-conscious concrete containing over 75% GGBS reduces the viaduct's carbon footprint by 60%, while the completed deck will allow flexible public space beneath. The decade-long engineering campaign has redefined underground construction. More than 23,000 workers deployed 11 tunnel boring machines to excavate over 80 kilometers of tunnels and caverns with remarkable precision. Each TBM operated as a moving factory, simultaneously excavating, installing precast concrete segment linings, and maintaining face stability through controlled pressure systems. In complex zones, road headers and excavators were used to shape station caverns and cross passages. Spoil removal, segment delivery, and ventilation were managed through continuous logistics systems deep underground. Speed meets precision in the delivery of a modular office building for Siemens in Krefeld, executed using advanced systems from Algeco. The structure consists of 160 prefabricated modules arranged across 4, fully equipped and assembled in an accelerated construction sequence. Each module arrives pre-fitted, enabling rapid stacking and integration on site. External features include Attica detailing in corporate colors, facade blinds, and lightning protection systems. Internally, the building incorporates access control, F90-rated fire protection zones, fire detection systems, and smoke control doors. Additional fit-out elements, such as flooring systems, kitchen installations, infrastructure, and compliant lighting, are integrated during fabrication. The result is a highly coordinated modular build, delivering speed without compromising technical performance or safety. Roofing efficiency reaches a new level with the Detention system, engineered for rapid tile installation without sacrificing precision. The method uses a structured support base that allows tiles to be aligned, clipped, and secured in sequence, minimizing manual adjustment. This streamlined workflow reduces installation time significantly while maintaining consistent spacing and load distribution. Ideal for large roof areas, the system enhances productivity and ensures a durable, weather-resistant finish. A clean, stone-finished facade begins with disciplined preparation and precise sequencing. The Clipstone Pro panel system is installed over OSB or plywood sheathing, starting with proper safety measures and surface readiness. Installation begins by fixing a starter strip along the sill plate using 1.25-inch No. 8 galvanized screws, ensuring perfect level alignment across the base of the wall. A water-resistive barrier is then applied in compliance with building codes, creating a protective layer against moisture intrusion. With the wall prepared, installation proceeds from the outside corners, where adjusted bottom clips allow panels to lock into the starter strip. Corner units are secured first, followed by flat panels. Each panel is aligned, slid tightly into position, and fastened with 3 screws, maintaining level consistency throughout. Where dimensional adjustments are required, panels are cut using a masonry blade grinder or saw, ensuring at least 2 clips remain for secure fastening. Subsequent rows interlock vertically, building upward in a continuous pattern. The system concludes with finishing such as wainscot sills, delivering a durable, mechanically fastened stone veneer without mortar, combining speed, consistency, and structural reliability. The BAMTech reinforcement system delivers a highly efficient method for installing rebar in slabs and walls, achieving productivity rates up to 10 times faster than traditional fixing. Each carpet consists of pre-spaced bars manufactured to exact design centers, with flexibility to incorporate varying diameters and custom lengths within a single unit. Installation begins with bottom mats, perimeter U-bars, and trimming details already in place. Wire high chairs are then positioned to support the top reinforcement layer. The top BAMTech carpets are rolled out rapidly, ensuring consistent spacing and structural accuracy. In this case, over 5.6 tons of top reinforcement were installed in just 54 minutes, while the total BAMTech quantity exceeded 10 tons within approximately 2 hours. This system minimizes labor, reduces errors, and enhances overall construction speed. The Innovacast mobile on-site casting system redefines concrete wall construction by shifting labor-intensive processes into a controlled, modular workflow. Traditional methods, precast and tilt-up, either require off-site transport or large casting areas, creating logistical and spatial inefficiencies. Innovacast addresses these constraints by utilizing compact site modules and vertical form systems, significantly reducing job site footprint. Each module integrates rebar, insulation, openings, and embedded components within a factory-controlled environment, ensuring consistent quality and minimizing field variability. Once delivered, modules are positioned vertically into form systems, allowing simultaneous casting of up to 7 panels. This vertical casting approach eliminates the need for slab casting areas, surface finishing, and extensive manual handling typical of tilt-up construction. A key technical advantage lies in accelerated curing cycles. Panels can be removed from forms in approximately 18 hours, compared to several days or weeks with conventional methods. By minimizing exposure to weather and consolidating processes, Innovacast enhances schedule reliability and structural consistency. The system optimizes labor deployment, enabling smaller crews to manage higher output across multiple projects. Through improved throughput, reduced site congestion, and enhanced safety conditions, Innovacast delivers a highly efficient alternative for modern concrete wall construction. The Rastignano Node Lot 2 marks the completion of the SP65 Della Fuda bypass, a key infrastructure upgrade designed to improve traffic flow and safety. Central to the project is a 263-meter steel viaduct configured with 5 spans, enabling efficient crossing of complex terrain while minimizing environmental impact. The structural system utilizes prefabricated steel elements, allowing rapid assembly and high precision during erection. Load distribution across multiple spans ensures stability and optimized performance under dynamic traffic conditions. Before commissioning, the viaduct underwent static load testing, typically involving controlled placement of heavy vehicles to verify structural behavior, deflection limits, and compliance with design specifications. These tests confirm the bridge's capacity to safely handle operational loads. Following successful testing, the project reached final completion and was open to traffic. This bypass enhances regional connectivity, reduces congestion in urban areas, and demonstrates modern bridge engineering through efficient design, controlled construction processes, and rigorous quality verification. Accurate steel fab demonstrates how panelized light-gauge steel framing is transforming construction speed and precision. Unlike volumetric modular construction, the focus is on panelization, where wall frames are fabricated off-site, stacked, and delivered ready for immediate erection. This enables vertical construction to begin as soon as slabs are completed, significantly compressing project timelines. Pre-punched service openings and tight tolerances, within approximately 1/8 inch, eliminate on-site adjustments common in timber framing. The system enhances quality by producing straight, warp-free structural elements while reducing material waste and labor demand. Integrated software and machinery ensure consistency, minimize downtime, and improve coordination across design, fabrication, and installation phases. By optimizing workflow and reducing uncertainties, panelized steel framing offers a scalable, efficient solution for multifamily, commercial, and industrial projects, positioning it as a key driver of modern construction innovation. Perfectly smooth walls could be achieved without manual skill, variability, or delays. The Waybuild intelligent plastering robot redefines finishing by turning a traditionally labor-intensive task into a precise, automated process. Driven by BIM-based planning and semantic data, the robot maps its workflow before execution. It navigates autonomously using SLAM technology and laser positioning, eliminating the need for pre-installed guides. A multi-sensor system combining IMU and vision ensures accurate positioning and stable operation. With built-in self-diagnostics and an integrated control system, the robot applies plaster uniformly, delivering consistent surface quality while significantly improving efficiency and reliability on modern construction sites. Material logistics for the second San Gottardo road tunnel represents a complex, high-capacity operation requiring continuous coordination and precision. A total of 7.2 million tons of excavated material must be handled using a just-in-time system, ensuring immediate removal from tunneling zones to maintain workflow efficiency. On the northern side at Goshen, compact facilities process up to 10,000 tons per day within a confined valley. Conveyor belts, silos, and loading systems are centrally controlled, synchronizing material flow, dust suppression, and train dispatch every 2 hours. On the southern side at Arolo, excavated rock is combined with incoming material via an extensive conveyor network, including routes through existing tunnels. Approximately half the material is processed into aggregates through crushing, washing, and screening systems, producing multiple fractions for concrete production at rates of up to 6,000 tons daily. Operating 24/7 under variable alpine conditions, the system integrates rail logistics, processing plants, and environmental reuse, ensuring uninterrupted tunnel construction progress. The next generation Hadrian X has successfully completed its first outdoor test build, marking a major step in automated masonry technology. Controlled via tablet, the system features a 32-meter telescopic boom capable of placing blocks up to 600 x 400 x 300 millimeters with high precision. A redesigned shuttle delivery system ensures continuous material supply, improving speed, accuracy, and operational reliability. Unlike traditional bricklaying, the system uses a specialized construction adhesive instead of mortar, enabling uninterrupted placement and enhancing structural performance. Its modular architecture allows rapid component replacement and customization to suit different project requirements. By combining robotics, automation, and advanced materials, Hadrian X significantly increases productivity while reducing labor dependency and construction time on modern building sites. What if a fully functional workspace could be assembled in a fraction of the time, without traditional framing, nails, or complex construction methods? The Tuin-Contour tiny house answers that question through the innovative Systember interlocking timber system, engineered for speed, precision, and sustainability. The assembly process is highly streamlined. Construction begins with a prepared foundation or slab, ensuring a level base for accurate installation. Prefabricated timber elements are then delivered to site and stacked sequentially, each component precisely milled to interlock with the next. Walls rise rapidly as the system relies on mechanical interlocking joints, eliminating the need for extensive fastening or wet trades. Beyond speed, the system delivers strong thermal performance. The solid timber configuration minimizes thermal bridging, improving insulation efficiency and indoor comfort. With most fabrication completed off-site, installation becomes a streamlined process, requiring fewer tools and less heavy equipment. From garden offices to compact living spaces, tiny house represents a shift toward modular, intelligent construction, where simplicity in assembly meets high-performance building standards. Construction of the main towers on the Kawasaki-Rinko Road progressed with meticulous planning and heavy lift operations. A 12 800-ton transport barge delivered the pre-assembled tower base to the site pier, where preparatory work for erection commenced. The 3,000-ton crane vessel Fuji entered via the Tsurumi waterway, ready for lifting operations. Specialized lifting equipment, including 60-meter loop slings with a 100-ton braking load, was prepared for hoisting. Rigging operations began, and the crane vessel was carefully maneuvered into position, secured with lashing to prevent sway. Precise alignment was achieved using tower positioning jacks, keeping installation tolerances within plus or minus 3 millimeters. Temporary erection pieces were fitted and tightened with high-strength bolts. The MP3 main tower lower blocks were installed, followed by water-shedding work and joint connections with plus or minus 4.5 millimeters precision. Subsequently, the MP3 middle blocks were placed, completing the lower two-thirds of the tower. Installation of the upper tower blocks, atop the PC girder, is scheduled for February to March 2026. Following assembly, lifting gear will be dismantled, and the crane vessel Fuji readied for departure, marking the successful progression of this complex maritime tower erection project. The road printer Echo, engineered by Zetra van Gelder with Klaaskuchen BV, uses a sideways conveyor system to transfer stones directly from the dismantled street to paving machines, eliminating transport through neighborhoods. Its compact design allows precise leveling and compaction, while fully electric operation removes the need for additional dumping and heavy machinery, ensuring efficient, safe, and sustainable street reconstruction. Concrete removal is streamlined using the MHB Badger breaker. Its precision-engineered hydraulic system efficiently fractures concrete, minimizing debris spread, reducing labor, and ensuring safe, controlled demolition for site preparation and material recycling. The TD500 exterior wall spraying robot revolutionizes high-altitude construction. Comprising suspension, spraying, and control systems, it delivers sandless latex, water-based, and multicolor paint with 3 to 5 times manual efficiency. Advanced trajectory planning, posture stability, and breakpoint resumption ensure precise, uniform coverage. Safety features: overspeed limit, overload monitoring, wind detection, eliminate manual high-altitude risks. With AC 380 volts power, IP54 protection, and one-key positioning, it guarantees efficient, reliable, Finlay train provided by Komatsu. This fully integrated crushing and screening setup is designed to deliver maximum efficiency, precision, and reliability across a range of applications. At its core are two J1175 jaw crushers, engineered for high-capacity primary crushing, complemented by two C-1550 plus cone crushers for secondary and tertiary reduction, ensuring consistent product sizing. The system features multiple screening units, including 893 plus and 883 plus scalping screens, and 693 plus and 694 plus incline screens, allowing precise separation of materials by size while maintaining high throughput. Material movement is seamlessly managed by the TC65 and TC80 tracked conveyors, along with the Trail 80 tracked radial conveyor, enabling continuous, smooth flow between crushing and screening stages. This configuration provides operators with a fully modular, mobile, and flexible solution, minimizing downtime and maximizing productivity. By combining Komatsu's engineering excellence with Bell's property management's operational expertise, the Finley train sets a new standard for efficiency, precision, and versatility in modern material processing. Across the vast landscape of India, the Samruddhi Expressway emerges as a benchmark in high-speed infrastructure. Stretching 701 kilometers, this ambitious corridor demanded a synchronized fleet from Virtgen Group to deliver unmatched paving precision. Hand compactors and tandem rollers established a stable foundation, while Vogel pavers ensured consistent asphalt layers. Kleemann screening systems optimized material gradation across the workflow. At the heart of the operation, 16 Virtgen SP 1600 slipform pavers executed continuous concrete placement with exceptional accuracy. Engineered for durability and low maintenance, the concrete surface supports speeds up to 150 km per hour, cutting travel time between Mumbai and Nagpur in half. The result is a seamless integration of performance, longevity, and ride quality. Rising along the outskirts of Delhi, the Eastern Peripheral Expressway stands as a model of precision-driven highway engineering. The operation begins with subgrade earthwork, where soil compactors establish a stable, load-bearing foundation. Tandem rollers follow, refining surface density to exact specifications. A carefully controlled layer of dry lean concrete is then placed using sensor pavers, forming a uniform base for the structural pavement. Concrete dumping and plow-based spreading systems ensure consistent material distribution ahead of paving. At the critical stage, slipform pavers, led by the SP 1600, deliver pavement-quality concrete with continuous, high-accuracy placement. Each phase is synchronized to maintain uninterrupted workflow, minimizing variability and maximizing output. The result is a durable, high-performance expressway engineered for longevity, reduced maintenance, and superior ride quality, executed by experienced contractors using advanced construction technologies. In the Swiss Alps, the Nantes-to-Drance grid connection was executed through a tightly controlled sequence of high-voltage engineering operations. The process centered on installing a dual 380 kV overhead line, involving precision tower erection, conductor stringing, and tension calibration across complex alpine terrain. Subsequent phases focused on system optimization, where existing SBB lines on the Salvan Plateau were dismantled and sections rerouted beamsaut underground cobbling toward Verniaz, requiring trenching, insulation layering, and thermal protection design. In parallel, legacy Swiss grid lines spanning the Rhone Valley were systematically removed, using staged deconstruction techniques to maintain grid stability. Each step demanded synchronization between civil works and electrical integration, ensuring continuous power flow while upgrading capacity, reliability, and environmental performance. The 2021 Commissioner Street Bridge Combined Project forms part of Toronto's large-scale Port Lands redevelopment, where multiple bridge structures were delivered as an integrated infrastructure system. The Commissioner Street Bridge, designed as a continuous steel girder structure, was engineered to accommodate complex site conditions, including contaminated soils and limited foundation capacity. A defining feature of this project was its off-site prefabrication strategy. Major bridge components were fabricated, fully welded, and painted in controlled factory environments before being transported by barge and installed on-site. This approach minimized on-site construction risks, improved quality control, and accelerated the schedule. Structurally, the bridge incorporates multiple piers to achieve continuous beam action, reducing stress on deck girders while optimizing load distribution. The design also prioritizes vertical load transfer, limiting lateral forces to suit challenging ground conditions. As part of a coordinated family of bridges, the Commissioner Street Bridge integrates seamlessly with adjacent crossings, supporting urban connectivity, flood protection, and long-term waterfront development, demonstrating a modern, systems-based approach to bridge engineering. An advanced inspection campaign was carried out on all 168 stay cables of the Jushan Bridge. Instead of conventional manual methods, 3 robotic systems were deployed to scan cables simultaneously, improving efficiency and eliminating major traffic interruptions. When anomalies were detected, immediate verification and condition assessment were performed. Inspection data was streamed directly to a digital twin system, enabling accurate monitoring, defect tracing, and a transition toward predictive maintenance for long-term structural reliability. The Parthenon on-site detention system by Australian Tanks demonstrates exceptional versatility in modern stormwater management. Designed as a modular underground solution, the system adapts efficiently to varying site constraints, making it suitable for both dense urban developments and large-scale infrastructure projects. Its lightweight yet durable components enable rapid installation, significantly reducing construction time and on-site labor requirements. Beyond speed, the system ensures high storage capacity and reliable water flow control, supporting compliance with stringent drainage regulations. The latest installation highlights how Parthenon technology streamlines project delivery while maintaining structural integrity and long-term performance, offering a highly efficient and scalable detention solution.